Okay, I intend this to be the last lecture video. There still might be quiz videos, but I will email you whenever I have a new quiz posted or new quiz video posted. All right, so our last topic I want to talk about is ring homomorphisms. So let's define that. Let R and S be rings. And a ring homomorphism is a function. So a function phi from R to S is a ring homomorphism if it satisfies two conditions. So, like we remember from group theory, a group homomorphism was a function between groups that turned one operation, the operation in the first group, into the operation in the second group. So the idea of being a homomorphism is about a function preserving operations. Well, in a ring, or in rings, we have two operations to worry about, addition and multiplication. So a ring homomorphism needs to preserve both operations. So for any, we'll call them A and B in the domain, phi of A plus B has to equal phi of A plus phi of B. So if I just have that, this would be a group homomorphism under addition, because both R and S would be groups under addition. If we preserve addition, this would be a group homomorphism. So to be a ring homomorphism, it's harder. There's a second condition that also has to be satisfied, which is it preserves multiplication. So phi of A times B, here this is multiplication in R, this equals phi of A times phi of B. All right, so ring homomorphisms preserve both operations, addition and multiplication. Okay, so before we get into examples, let me do the related definitions. Kernel of phi. So it's the same phi from the previous board. It's a function from R to S. So the kernel, just like it was in the group homomorphism definition, the kernel is the set of things in the domain that get sent to the trivial element. Here the trivial element is the 0 element. So this would be all of the x's in R such that phi of x equals 0, but just for clarity, that 0 is the 0 in the output ring S. That's 0 sub S. Right? So it's the set of all elements that get mapped to 0. I guess I should, well, so the theorem is that kernel phi is an ideal of R. So let's prove that with our ideal test. Let me state this next thing first. Well, we technically already know it, I guess. So first thing, if I want to prove something is an ideal, there were two conditions we have to check, but there's also the fact that it's non-empty. So we have to show that this is non-empty. Kernel phi is not empty because phi of 0 sub r is equal to 0 sub s. So 0 sub r is an element of the kernel. Okay, so I can come back and prove this, but we technically have seen this elsewhere. This statement here, that phi of 0 equals 0, that's basically a fact from group homomorphisms. So if you remember, if you think back, for group homomorphisms, we have this property that if you apply a group homomorphism to the identity element in the domain group and in the input group, the output is the identity element in the output group. So like I said before, ring homomorphisms are also group homomorphisms under addition. So under addition, the identity elements are 0 elements. So phi of the domain identity equals the output identity. So phi takes additive identity to additive identity. Okay, so let's just state that here for now. So it's non-empty. Let me erase. Let's check that it's closed under subtraction. So we let pick two elements from the kernel, A and B. That means phi of A equals 0s and phi of B equals 0s because they're both elements of the kernel. So now let's check what is phi of A minus B. We want to show that A minus B is in the kernel. Well, phi is a ring homomorphism, which means it preserves addition. Subtraction is just a notation that indicates a certain addition here. So I'll do it in a couple steps at least. We've proven this stuff back in group homomorphisms, but let's do it carefully here. Phi of A plus negative B is what A minus B means. So that's phi of A plus phi of negative B, because ring homomorphisms preserve addition. Again, it's a property from group homomorphisms that they preserve inverses. Well, negative B is the inverse of B under addition. So as a group homomorphism, phi, you can transfer this minus sign out. So this would be phi of A plus negative phi of B. But that just means phi of A minus phi of B. But both of those are 0. So that's 0 minus 0, which is 0. So therefore, let me squeeze it in here before I erase. Phi of A minus B equals 0. Therefore, A minus B is an element of the kernel of phi. That's a phi. Okay, so it's closed under subtraction. And so basically that part of the proof is our proof from earlier in the course where we proved that kernels of group homomorphisms were subgroups. But to show it's an ideal, we have to do more than that. So the second part of the ideal test is I take an element from the kernel, so let A be an element of kernel phi, and I take a second element but out of the big ring R, so let little r be an element of capital R. I need to show, since I don't know this is a commutative ring, I need to show that A times R is in the kernel and I need to show that R times A is in the kernel. So let's do one of them. They're similar. The two arguments are virtually identical. But to show something's in the kernel, in this case, A times R, I want to show that's in the kernel, so I look at what happens if I apply phi to it. So phi of AR. It's a ring homomorphism, so I can split this multiplication up. Phi of A times phi of R. I don't know anything about phi of R. However, phi of A, since A is in the kernel, phi of A is 0. So this is 0 sub S times phi of R. I don't know what phi of R is, but I don't care, because if I multiply by 0, I get 0. So that equals 0. No, sorry, 0 R. So phi of AR equals 0. Therefore, AR is an element of the kernel. And similarly, I won't write it, but similarly, R times A is an element of the kernel. So it's an identical argument. It's just, it would be phi of R times 0, which we know would be 0. All right. So kernel of phi is an ideal. Let me briefly comment on the other one. So phi, since it's been a few boards by now, phi was a function from R to S. Kernel phi lives in the domain and is an ideal there. We also had, if you think back to the group homomorphism stuff, the phi of R, so the range of this function. This is defined the same as it was for group homomorphisms. This is the set of everything in S, so we'll call it set of Y in S, such that there exists an X in R, such that phi of X equals Y. Okay, so this is a subset of S. I won't prove it, but phi of R is usually, well, not necessarily, it's not necessarily an ideal of S. It is, however, a subring of S. Okay, so it lives in S as a subring. It's not usually an ideal, or not generally an ideal, which means you can find an element in S that's not in this, so that when you multiply the two, you don't land back in this. Okay, so let's do a couple examples of ring homomorphisms. These are a little bit harder to find examples. So one example is our modding function. So if I take the function from the integers to the integers mod n, given by phi of x equals x mod n, that's a ring homomorphism. It preserves addition. Addition in the integers turns into addition mod n, and multiplication in the integers turns into multiplication mod n. So it preserves the operations. The kernel of this phi would be the set of everything that gets mapped to 0. So everything that when you mod by n becomes 0. Those would be multiples of n. So the kernel would be nz. So the integer multiples of n. Okay, so that example was also an example of a group homomorphism under addition, but it is a homomorphism that also preserves multiplication. All right. So that one is a homomorphism, is a ring homomorphism. Let's look at an easy example that was a group homomorphism but is not a ring homomorphism. So if I took the function from z to itself, given by phi of x equals 2 times x, and ask, is this a ring homomorphism? Well, we check two things. We look at phi of a plus b. Phi of a plus b would be 2 times a plus b, because phi just multiplies the input by 2. And then I can distribute the 2 as 2a plus 2b. And 2a plus 2b is phi of a plus phi of b. So it preserves addition. So that tells us that this is a group homomorphism under the group operation of addition. But what about multiplication? If I look at phi of AB, that's by definition 2 times AB. And in general, this is not going to be the same thing as 2a times 2b. For specific a or b, it might. Like if one of the two numbers is 0, then yes, these would be the same. But in general, this is not the same thing as this for arbitrary a and b. I could find specific examples where it wasn't equal. So these are not the same. This is what I'd get if it was a ring homomorphism. That's phi of a times phi of b. So these are not equal in general, which means this is not a ring homomorphism. And it's because this fails here. This condition fails. So even just simple linear functions, so a very basic linear function between integers here, that's not a ring homomorphism. Right? Let's do one of the most important examples of ring homomorphism. I've been trying to emphasize that ring theory, we're not going to get any deeper into it, but one of the motivating reasons for ring theory is the study of polynomials. So, let me do this one first. If we've got the polynomial ring Zx, and I want a function to Z, this will be, I'll give it a name in a second, but here's the function. I have a polynomial f of x. So that's a polynomial in the variable x with integer coefficients. The function, the homomorphism I want to define here is called an evaluation function. So I'm going to call this EV, and basically what it's doing is I'm choosing a specific integer and I want to plug it into this polynomial in place of x. So this will be, let a be an integer, EV sub a, that's the name of my homomorphism. What it is it takes a polynomial, f of x, and it just takes this integer a and plugs it into the polynomial as if it was a function. So I take f of a. Okay, so let's do a specific example here. So say it was 2, EV2. So I don't need to say let 2 be an integer. 2 is just an integer. So what this is doing is an input, so the function is ev sub 2, evaluation at 2. The input of that function is a polynomial. So suppose it was 4x squared minus 3x plus 6. That's a polynomial. That's an element of zx. So ev sub 2 of that is, I'm going to plug in 2 in place of all the x's. That'll give me a computation in z, and that'll simplify to just give me an integer. So it'll be 4 times 2 squared minus 3 times 2 plus 6. That's 16 minus 6 plus 6, so 16. So EV2 of this polynomial is 16. EV of a different polynomial, say x cubed minus 5x plus 7. I'm still plugging 2 in, because the function is dependent on 2, is determined by 2. I plug 2 in for these x's. That's 2 cubed minus 5 times 2 plus 7. So that's 8 minus 10 plus 7. That'll be 5. So any integer polynomial that I could make up, we have an output associated by this function. Okay, but, and this will take more explanation, but let's just do it. If I have, let's is this a homomorphism? So there's subtle stuff going on here. Let me just do it according to what we know from algebra and wherever. If I'm adding two polynomials, I'm just combining like terms. If I want to plug in a value, it doesn't matter if I plug it in before I combine like terms or after I combine like terms. Okay, so the addition here is taking two separate polynomials and adding up their like terms. Then the evaluation function would take that polynomial and plug in 2 to the x's. But I get the same answer if I plug in 2 to f and I plug in 2 to g. I plug them in separately and then add my two numbers. Okay. So this side of the equation, if I wait till after I add them and then evaluate, that's after I combine all my like terms to get a single simplified polynomial. The right side, that is taking the two separate polynomials, plugging in 2 and calculating, and then adding up the two numbers. Because of the properties of integers and commutativity and all that stuff of multiplication, we'll get into it. That's going to give me the same answer. Same with multiplication. If I multiply two polynomials and simplify it and then plug in 2, I will get the same answer, the same number, as if I plug in 2 to the first polynomial and I plug in 2 to the second polynomial and multiply those two things. Okay, so I haven't really proven anything. I've just written easy facts that we take for granted, that we don't even question for the integers, and just writing them in terms of saying this function is a homomorphism, is a ring homomorphism. Okay, so I'll say more in the more general context. So these evaluation maps, they are, in the right conditions, they are ring homomorphisms. Before I move on to the general version, let's ask for this specific one. What is the kernel for this function? The kernel of EV2. So it would be the set of polynomials for which f of 2 is 0. So let me write that out. This would be all of the polynomials f of x in Zx such that f of 2 equals 0. We've seen this before in the couple videos ago. A set of integer polynomials for which f of 2 is 0, that would be the set of polynomials for which x minus 2 is a factor. So you can factor out x minus 2 from the polynomial if 2 is a root. That's a fact from college algebra if you want to go back that far. But our name for it was this. It was the ideal generated by x minus 2. That's the collection of polynomials that have x minus 2 as a factor. Right. Okay, so because this polynomial stuff is important, let me kind of repeat what I did there for that specific function, but in the more general case. So what we want, let R be a commutative ring we don't need unity necessarily. And let A be an element of R, then we can define an evaluation function, EV sub A, from the ring's polynomial ring, Rx, to the underlying ring R. And so it's just plugging an x value in, taking a polynomial f of x in the polynomial ring and plugging this A in place of x. So that's f of A. Okay. All right. We can do more example with a less familiar ring in a second. But actually, let's illustrate this with a simple, easy example, but not as familiar as the integers. So suppose we do like a z mod n example. So we'll go from z5x to z5, and I have to pick a number from 0 through 4, so let's say 3. So let's take a polynomial in z5x. So we'll say 4x squared plus 2x plus 1. EV3 of that, we're plugging 3 in every place of x. And now we have this computation, but that computation is occurring in Z5. So it's occurring mod 5. So 3 squared is 9. Mod 5 is 4. That's 4 times 4. 2 times 3 is 6, but mod 5, that's 1. Plus 1. 4 times 4 is 16. Mod 5, that's 1. So I have 1 plus 1 plus 1, which is 3. So whatever polynomial I have here, if I plug 3 into it, I can simplify that mod 5 and get an integer mod 5. Okay, but my real reason for doing this is to argue that, yeah, I don't need to have the specifics for this part. My real reason for this is to make it clear why this is going to be a ring homomorphism. Addition addition is easier than multiplication, so let's focus on multiplication because that's the new stuff. Addition is just combining like terms, and you don't have to really convince yourself of that. It's really about multiplication. So let me take a generic looking a generic polynomial, but let's just make it like degree 1. So make linear polynomials here. So this is just an illustration. I don't want to call it a separate example. I want to show that the evaluation map preserves multiplication. I want to argue that, but I want to do it just by illustration. So suppose I have two of these things. We'll say R. I'm going to run out of R1x plus R2. So there's one polynomial. And I have a second polynomial like S1x plus S2, where these R's and S's are just coefficients coming from the ring R. Okay, so if I multiply this, polynomial, I haven't plugged in anything for x yet. I just take these as polynomials and I multiply them first. I basically use the FOIL method. I do R1x times S1x and then R1x S2 plus R2 times S1x plus R2 S2. Okay. Then our rule for multiplying polynomials is, the way I simplify one of these is I just group the x's together and make this x squared, and I multiply their coefficients, R1, S1. And then I combine these like terms. I multiply the coefficients together, so that's R1, S2. And I have R2, S1. And that's all times x, and then plus R2, S2. So as I'm multiplying these polynomials, it's just my rule for how do I multiply polynomials that tells me in any monomial, when I'm multiplying two monomials, I combine the x's, however many x's I have, I put them together with an exponent, and I multiply their coefficients. And I combine any like terms if they have the same x power. Okay? We're treating x like a formal variable that's just keeping track of which term we're looking at. And so that's the rule for how do we multiply polynomials. Now, what happens if I plug in a value for x? If I plug in a, well, now it's no longer a formal variable x. It becomes an a. And so in my expansion here, let me replace all my x's with a's. And let me not write the next one just yet. So if I look at this, now it's not an abstraction anymore. This expression here, R1a S1a, that's a product of four things coming from the ring R. I can't just magically put the a's together unless I know that R is commutative. But since R is commutative, I can rearrange the factors in this product however I want. So I can put the a's together and I get a squared, and I put R1 and S1 together in front of it. Same thing here. A's in the middle. I couldn't move it past this unless I know that it commutes with everything because R is a commutative ring. So I can move the A out front, or sorry, out back, whatever. Same thing here. I can put these together, and this ends up combining like this by the distributive property. Okay, so when we say things like the evaluation map is a ring homomorphism, that relies on the underlying ring being commutative, because when we replace x with a value from the ring, we go from the formal definition of multiplying polynomials to the concrete definition, or the concrete notion of multiplying, of computing things with multiplication and addition within a ring. So if everything commutes, this product will turn into this expanded form here. And so it doesn't matter if I think of this a, if this a is an actual value or if it was the variable x. Everything commutes, so it simplifies like this in either case. So plugging it in first before I multiply is the same as plugging in after I multiply. So this example is just intended to illustrate the issue. It's true for higher degree polynomials as well. So the higher powers of x and so on. All right. So hopefully that wasn't too confusing. Yeah, so the point there, I should have written it down. When R is commutative, that evaluation map I just wrote is a ring homomorphism. If R is not commutative, then it's generally not a homomorphism. It could be for specific A values. Like if you find an A which does commute with every other element of the ring, that should be fine. That should work, yeah. But you have to be more careful with it. Okay. So let me talk a little bit about the first isomorphism theorem for rings. First isomorphism theorem for rings. So let phi from R to S be a homomorphism, be a ring homomorphism. Then I guess I didn't define this, but R mod the kernel of phi is isomorphic to phi of R. I didn't write down what a ring isomorphism is. It's just a ring homomorphism which is also bijective, just like it was for group isomorphisms. So what this means is, as rings, this ring is the same as this ring. We're just renaming the elements and possibly renaming the operations. So ring isomorphisms, two rings are isomorphic if they are essentially the same ring. There's a one-to-one function between them that preserves all of the operations. One-to-one and onto function between them that preserves the operation. Okay, so the idea here is virtually identical to the first isomorphism theorem for groups. I'm not going to prove it here either. I said a little bit for groups, but I'm not going to do anything extra here. But just to remind you of the idea, we've got a function from R to S and we've got a function, I guess I need some more. Function from R to S, we're assuming it's a ring homomorphism, so it preserves operations. We want to make it an isomorphism, so we have to do two things. One, this is not onto because I'm missing some of the elements in S. I'm not hitting all the elements of S. So by restricting to phi of R, I'm forgetting all of the outputs that don't actually get used. All of the elements of S that don't actually get used as outputs. So that forces it to be onto. Then I also have to force it to be one-to-one. I do that by gluing things together if they share the same output. So if these two inputs have the same output, the function is not one-to-one, but I can fix that if I make sure that I always glue these together to make one bigger element that goes to one element. And that's what happens when we're doing a factor ring construction. If I mod out by the kernel, that's gluing things together if they have the same output. Okay, so we talked about that with groups, but let's just use it on a concrete example. It has to do with polynomials. This will probably be the last thing I do for this. Okay, so I want to look at real number polynomials. So Rx, those are polynomials with real number coefficients. And I want to mod out by the ideal generated by x squared plus 1. Okay. So let's talk about this intuitively for a second, and then I'll tell you what this is isomorphic to, what this factoring is equivalent to, and then I'll give you a proof based off of the first isomorphism theorem that I just wrote. All right. So as we've talked about, when I'm modding out by some ideal or a subgroup in the group case, when I'm modding out by an ideal here, we're essentially saying this element, and therefore everything it generates, this element turns into 0. So by doing this, I'm saying essentially I want to force x squared plus 1 to equal 0. When I mod by this polynomial, I'm forcing x squared plus 1 to equal 0 in the abstract. Well, if x squared plus 1 equals 0, that tells me x squared needs to be equivalent to negative 1. And that tells me that x should be equivalent to the square root of negative 1, which is our imaginary number I. Okay, so this is informal here. We're not actually saying that x squared plus 1 equals 0. We want to make it happen, essentially. But this thought process tells us that if I have all polynomials with real coefficients and I turn x into I, then every polynomial turns into a complex number with a bunch of i's and powers of I, which then can be simplified. So what we want to say is this factoring turns out to be isomorphic to the complex numbers. As rings. They're isomorphic as rings. Okay, so let's prove this. I'm going to use the first isomorphism theorem. So that means I need to come up with a function from Rx to the complex numbers that has this as its kernel. All right, so we want to go from Rx to the complex numbers. And the function is, this is a little bit of a clash with my definition earlier, but the thought process is, just like what I erased here, I want to replace x with I. I want x to turn into the imaginary number I. So let's do this. Let's call this the evaluation function at I. So EV sub I of a polynomial f of x is f of I. So let's just do a quick example before to illustrate it. A quick example to illustrate this function. EV sub I of the polynomial 5x cubed minus 2x squared plus x plus 7. I'm going to replace all the x's with i's. That's what this homomorphism does. It'll be 5i cubed minus 2i squared plus I plus 7. And then going back to algebra to review I, I squared is negative 1. So I squared becomes negative 1, so this becomes plus 2 plus I plus 7. I cubed would be negative I. So yeah, I squared is negative 1. I have 1 I left over, so that gives me a minus sign, minus 5I. So the I squared turns into negative. I have 1 I left over, so negative 5I. Now simplifying, I've got 2 plus 7 is 9. Negative 5I plus I is minus 4I. So there's my simplified complex number when I plug I into this specific polynomial. So any polynomial with real coefficients, if I replace all the x's with I will get some complex number. And since I commutes under multiplication with real numbers, that's going to be a ring homomorphism, so I don't have to worry about that. Okay, so that's how the function works. Now, what's its kernel? Let's do the range first. What is EVI of this entire domain? Well, I claim it's the complex numbers, and that's because if I take an arbitrary complex number, it's going to look like a plus bi for some a and b in the real numbers. Well, how do I get that as an output of this function? I just take ev sub I and apply it to the function a plus bx. So a plus bx, that is a polynomial in Rx. If I use the evaluation function where x turns into I, then clearly it becomes a plus bi. So my range is C, is the complex numbers. So it's already onto already. It's not one-to-one. We get the same complex number with different polynomials, but we can figure out the kernel, and it's going to be this. So what's the kernel? Kernel of EV sub I. Let's run through it. It's the set of every f of x in the polynomial ring Rx such that f of I is 0. Okay, so this is the tricky part that we have to review some college algebra. So we're dealing with a real number polynomial for which I is a root. So from college algebra, if I is a root, of f of x, then x minus I is a factor. I'm going to have to erase something here. So if I is a root of f of x, then x minus I is a factor. But I can't say that x minus I, the ideal x minus I, generated by x minus I can't say that's the kernel because this is not an element of Rx. It has a coefficient that's not a real number. It has an imaginary coefficient. So that's not an ideal of Rx. But let's just do the short version. If I is a root of f of x, there was a fact in college algebra, however long ago you took that. If you have a complex root to a real polynomial, its complex conjugate also has to be a root. And the conjugate of I is minus I. The conjugate is you take the imaginary part and you flip its sign. So plus I, the conjugate is minus I. So minus I is a root, is also a root. So x minus negative I, which would be x plus I, is also a factor. Of f of x. So that tells us if f of x is in the kernel of this evaluation function, ev sub I, then x minus I and x plus I are both factors of f of x. So their product, x minus I times x plus I, is a factor of f of x, because individually they both have to be factors of f of x. But what's their product? If I multiply this out, that's x squared minus ix plus ix. Those cancel. Minus I times plus I is negative I squared. That's plus 1. X squared plus 1 is a factor of f of x. So, if this is a factor of f of x, that tells me f of x is an element of this ideal. So, therefore f of x belongs to this ideal generated by x squared plus 1. So if I follow my logic here, that tells us we've got the kernel of ev sub I is contained in this ideal. So we have one direction. The other direction, that this ideal is contained in the kernel, that's significantly easier, although I'm taking longer than I intended. If something is in this ideal, that tells us that x squared plus 1 is a factor. If x squared plus 1 is a factor, and I plug I in for x, I squared plus 1 is 0. So any function that has this as a factor is going to have I as a root, so it'll be in the kernel of EVI. So I'll cheat and say similarly, this is contained in this. EV sub I. So therefore they're equal. So by the first isomorphism theorem, the original domain mod the kernel is isomorphic to the range, which was the complex numbers. All right. So yeah, we'll leave it at that. So let's wrap this up. All right, let me try to end this one more time. This will be the last lecture video. Depending on when you're viewing it, there may still be 1 or 2 more quiz videos that are forthcoming. I will email you whenever those get posted, whenever I post something new on Blackboard. But in any case, do your best to attempt the problems that I assign from the book and to do whatever quizzes I post for you. Those will be more reflective of the kinds of things that I would put on whatever I end up doing for the remaining exams. All right, any other details that I need to announce or clarify, I'll send as emails. But let me know if you have any questions.